Code conversion. Objective: to design and implement 4-bit binary to gray code converter, gray to binary code converter. Binary to gray code converter combinational design procedure. We require 3 logic gates for converting binary to gray code, that is 3 XOR gates. The most significant bit of the gray code will be exactly equal to the first bit of the given binary number. Now the second bit of the code will be exclusive OR of the first and second bit of the given binary number. That is, if both the bits are same and the result will be 0, and if they are different the result will be 1. The third bit of gray code will be equal to the exclusive OR of the second and third bit of the given binary number. Thus the binary to gray code conversion goes on. Here is the circuit designed. Here the input variables are B3, B2, B1, B0, and output variables are G3, G2, G0, G1, where B is binary input, G is gray code in output. Now the truth table is shown, where binary input has B0, B1, B2, B3, and gray code output has G0, G1, G2, G3, which is both input and output. Here is the conversion of binary to gray code. Now let's see the Boolean expression. Using K-map, we have find the Boolean expression. To design the circuit, the components required are 4 input switches, 3 XOR gate. The following circuit design is shown at the end of the video. Now gray code to binary converter combinational design procedure. The most significant of the binary number will be equal to the most significant bit of the given gray code. Now if the second gray bit is 0, the second binary bit will be same as the previous or the first bit. If the gray bit is 1 and the second binary bit will alter. If it was 1 it will be 0, and if it was 0 it will be 1. This step is continued for all the bits to do the gray code to binary conversion. The circuit design is shown well here. Here the input variables and output variables is switched where it is opposite to binary to gray converter. Here input variables G3, G2, G1, G0, and output variables is B3, B2, B1, B0. Now let's see the truth table where you can find a clear information. Here G3, G2, G1, G0 are the gray code inputs, and B1, B2, B3, B0 are the binary code outputs. And using K-map for B3, B2, B1, B0, we have find the Boolean expression for the table. To design the circuit, the components used are 4 input switches, 3 XOR gate. Designed circuit is shown in the following. Encoder and decoder. Aim to design and implement encoder and decoder using logic gates. Encoder 4 to 2 line encoder. Combinational design procedure explanation using block diagram. In 4 to 2 line encoder, there are total of 4 inputs and 2 outputs. Here the input and output variables are y3, y2, y1, y0 and a1, a0. It is a 4 to 2 line encoder where the inputs are y3, y2, y1, y0 and outputs are a1 and a0. Here is the truth table shown. Logical expression for a0 and a1 is as follows. a1 is equal to y3 plus y2, a0 is equal to y3 plus y1, which is the logical expression. To design the circuit, the components required are 3 input switches, 2 OR gates. Whereas decoder 2 to 4 line decoder, combinational design procedure explanation using block diagram. In 2 to 4 line decoder, there are total of 3 inputs and 4 outputs. Input and output variables a0, a1, e are the inputs and y0, y1, y2, y3 are the outputs. It is a 2 to 4 decoder where a1, a0, e are the inputs and y3, y2, y1, y0 are the outputs. Here is the truth table shown clearly. The logical expression is as follows. y3 is equal to e into a1 into a0, y2 is equal to e into a1 dot a0, y1 is equal to a1 dash a0, y0 is equal to e into a1 dash a0 dash. To design the circuit, the components required are 2 input switches, 2 NOT gates and 4 AND gates. The circuit is designed in the following.